So I think we've had a few questions about interference colours. So let's move on to those. Of course, this thin section here, this image shows some beautiful interference colours, and there is a very strong variation across the slide here from the bottom left-hand corner to the top right. And that particular change in colour there, from a kind of orangey yellow right the way up to pale green, very pale green, through blues and pinks, that is purely a result of a very badly made thin section, which is much thinner down in this lower left-hand corner. So it's showing much lower order colours and much thicker up in the top right corner. So essentially it's a kind of a wedge-shaped thin section, not very well made. So let's have a look at some interference colours. If we go back to the hornblende that we looked at, this is from the same rock, although it's a different view. But again, you've got the sort of blue-green, and you've got the sort of more green, grass green sections, and then you've got the straw yellow or tan or almost colourless sections. And that's in plane polarised light. But what you see when you put those into cross polars is that those different sections have different colours. So this one is a very low order colour, a grey, the same one up here. But the more prismatic sections, this one was the colourless one, or near colourless one in plane polarised light, has a very high second order blue colour. And then the other section along here, it's a long thin prism here, has a rather lower second order colour there, which is a kind of pinky orange. Now I know that one of the tutors, Julie Dorr, came up with a fabulous analogy here, so I've stolen that, but I thought I'd better acknowledge her, as we should do, which is the different ways of cutting through carrots is very similar to the way that thin sections cut through crystals. And so in any thin section you will have not quite completely random orientation of cuts through crystals, but particularly in a metamorphic rock they might be lined up. But in an igneous rock they can be utterly random, and so you will see all sorts of different pleochroic colours if it's pleochroic, and you will see all sorts of different interference colours. So the key thing when on your mineral identification chart it says that muscovite or that hornblende has second order blue colours, of course not all the crystals will have in your thin section. They will run right the way from, you know, a low first order grey like this one in the middle here, right the way up to somewhere near this second order blue colour. So the key is always to look for the highest order colour that you can find for that particular mineral. You can essentially more or less ignore the lower order colours, the greys and so on, and just look for the highest order colour. So how do we tell what the highest order colour is? Well, partly you can use the chart, and I'll come on to the chart just in a bit, but there is a little trick that you can use with some grains, and to do that we need to zoom into this little bit of an amphibole crystal just here at the end, the ragged end of the crystal. And if we zoom in a little to this, you can see that at the bottom of this crystal there's a white patch. Now that's not a different mineral, that's part of the amphibole just in here, and it's a part of the amphibole crystal that is very, very thin. So it's kind of like a sliced oblique edge, like a sort of chisel edge, if you like, a beveled edge. And you can follow then through the thinnest part of the crystal, which has the lowest order colours, through white up into yellow, and then orange and red, and what we call the sensitive tint, which is this kind of glorious pink colour, and then through that and into the highest order colour, which is this kind of palish blue. And I've marked that on the chart at the bottom here. You see you start off in a kind of pale grey, and you go through the white, you hit the yellow, and then fairly rapidly through the red and the pink, purple, and then up into that pale blue, that sort of pale sky blue. So these beveled edges, these wedge-shaped edges of crystals, they're not that common in thin sections, but wherever you see them, they're extremely useful. And again, you know, it is a question of picking out the crystal shapes. And it helps, of course, at this point, it'd be lovely to be able to flick back to the plane polarized light view and to say, okay, yes, we can see that this crystal here, this blue crystal here, that is one definite crystal, and it is separate from the others. But then There are other areas of the slide, for instance, this sort of just to the right of this end crystal in here, just inside the circle, which are very confused, and you'd be hard-pressed really to say exactly what you're seeing there. It's probably the ragged edge of a very irregular crystal. So in some cases it's cut right through that crystal, it's looking through to the crystal underneath. You might be seeing inclusions, you might be seeing just a bit of crystal that's broken, that's actually been fractured and moved around during the slide making process. So really, really tricky. So that's quite a neat trick of looking at crystal edges if you're trying to find the maximum color, is to pick a beveled edge if you can, and then you can trace your way up the color chart to see where you are. So here are a few more examples of that. These are really quite nice examples. The one on the right actually is one that you have in the virtual microscope under, I think it's the only thing under the miscellaneous category. And the reason it's in there is to show you this kind of beveled edge trick of looking from the lowest order colors on the edge of the crystal where it's thinnest, and then tracking your way up through all the orders, first, second, third, and fourth, until you get to this top panel, which is where the crystal is thickest, and that is up in the fourth order pink. Now it is, yeah, assigning order is very difficult, and that again is something that comes with practice partly, and it also helps if you have a good chart. I've seen some absolutely shocking charts on the internet when I was looking for a decent chart. This is actually from the OU's online materials themselves. They tend to become, I think of it as becoming less and less primary, whether it was their reproduction or they just, you know, I looked at them and I thought that bears no relationship to what the colors actually look like. What I reckon is that you tend to see first order colors are very much primary colors, you know, black, grey, white, yellow, and red, very definite red. And then you hit the first, what we call sensitive tint, the magenta, which marks the boundary of the order. And in the second order, they're still fairly vivid, but I think of them as being a little more pastel. So they're a little more gradational, a little more pastel. So you go through a kind of nice sky blue, and then a sort of aquamarine almost, and into a kind of quite pastel-y yellow, and then orange, and so on, until you get up to the magenta that leads you into the third order colors. And by the time you get into third order, then you really are talking about very, very odd, slightly washed out colors, which are very much more pastel. And there, the colors, I don't know why this is, but the colors seem to be much more restricted to more or less this funny sort of green, pale green, and a pink. And it is actually quite difficult to see many of the other colors in there. And then in fourth order, that becomes even more pronounced. So very pastel shades, quite dull really. And once you get into fifth and above, you're looking at colors that are so washed out that they're almost white, and we'll come on to that. So here I've just really tried to show three examples. I can't even remember what minerals these are. I think the first two are both pyroxenes, I think. No, sorry, pyroxene on the left. I think this is actually an olivine in the middle, and then this is a slice of gypsum. And I've tried to represent exactly what you see, in a sense, from going from the thin part of the crystal at the thin end of the wedge up to the maximum color. And essentially that tells you, that shows you the maximum color at that beveled edge. And you can see these bands of color here really quite nicely. Sometimes they're quite narrow, and sometimes they're quite broad, and you can actually see, sort of pick your way through them. So I found that really quite a useful way of defining what the maximum color is. So this is really going from greys, which is typical first order colors, and then hornblende, particularly amphiboles, shows a lot of first order reds and oranges and yellows, but its maximum color will run up to something like in this second panel here, which is a kind of bluish or even a bluish, slightly bluish green, like this one down the bottom here. Third mineral here, this is actually epidote, and epidote has quite rather psychedelic colors. And this maximum color here, this shows you a kind of almost typical third order in that you haven't really got any colors there except just a sort of purple and a green. So you're really just looking at that sort of straddling part of the third order in here, running from purple to green. That's all you've got in there. So that's in third order. biotite shows colours which are very, very strongly confused or masked by its brown colour. And so, in fact, in this one here, shows this effect least because this biotite crystal is running north-south. We'll come back to that later, but that means that in plain polarized light it would have a very pale colour. And so the interference colours for once show up quite nicely. And here those interference colours are a mix of sort of pinkish at the bottom here and more greenish, or a mixture of green and pink as you go further up the crystal, which probably means that that crystal in the thin section is getting thicker as you run from the bottom to the top. So that places it somewhere up at the top of the third order. And then on the right-hand side here, interference colours are kind of diagnostic. You can get it in metamorphic rocks, but you can also get it in sedimentary rocks, and not that commonly in igneous. Calcite, yeah. So calcite shows these very strange colours, which you sometimes get a kind of iridescent play of very kind of psychedelic colours, but still fairly washed out. But most of the time it just shows this kind of very, very washed out, almost pearlescent type of effect. So it's not quite white, but it's a kind of pearlescent, very, very, very washed out pale colours. And that's kind of very typical. Now the other thing about, since I've managed to pick a view that was reasonable here, is have a look at this grain in the middle of that calcite. This is a marble, a metamorphic rock, so it's made almost entirely of calcite in this case. But there is a grain in here that looks very different in the middle, that kind of rounded, blobby, dark grain. Now that grain is actually calcite as well, but it's calcite that is in extinction. So it's in one of these 90-degree positions as you rotate the stage that happens to put that crystal into extinction, and essentially the crystal is in an orientation that cuts out all the polarized light. And in most minerals it cuts out all the light, but in calcite shows a very diagnostic property which can be really useful for identifying it, which is called, well, we call it bird's eye extinction. I really don't know why we call it that, because it doesn't look anything like a bird's eye, but it is this kind of incomplete or imperfect extinction where the crystal doesn't go completely black, uniformly black. It looks a bit like I think it looks a bit like a starry sky, kind of all twinkling with stars, paler patches and white patches and white spots within a black background. So that bird's eye extinction is a very characteristic property of calcite, but we can also use it for other minerals, and I'll come on to that. Okay, we'll move swiftly on. So interference colours, I just want to say just very briefly again about biotite muscovite, which of course it should be easy to tell apart in plain polarized light. But in cross-polarized light, you can get quite confused if you're flipping between the two. But they do show rather different orders of colour. The biotite is usually much higher, somewhere up in the fourth order around here. But the muscovite is usually much lower. It's usually in the third order, and very, very commonly has this kind of turquoise colour. That's a really common colour for muscovite to have. So you can usually see the difference between the two in cross-polars in thin section. Tell me what this crystal here, this is also muscovite, tell me what that is showing, what property that is showing in this particular cross-polarized view. In fact, this shows pretty much exactly the same sort of extinction as calcite. It's bird's eye extinction again. So if you look in here, you can see it's got a kind of texture to it again, and you can see that it's not uniformly black. It's not quite straight, to be fair, but it is not uniformly black. You've got these speckles of white and pale grey all the way through it, and so that is very characteristic of mica as well. So both the micas and calcite show this bird's eye extinction, and it can be extremely useful for telling micas apart from other minerals. So there you go, that's the same view in plain polarized light. Of course it's dead easy to see the difference between the biotite and the muscovite as well, but muscovite can be quite tricky to pick up because it's colourless, and if it doesn't have a very good shape, for example, if it doesn't have these lovely lath-like shapes, then it can be quite tricky to spot. But if you can spot the bird's eye extinction, and it's basically any section of muscovite will have this bird's eye extinction. It's not orientation dependent. then that is a really useful diagnostic property. Okay, so another thing about interference colours, and this is something you see with calcite, but with some minerals they have very strong colour, and I talked about biotite masking the colour of biotite masks the colour, the interference colour. And here's another mineral where that's true as well. But luckily titanite has such high interference colours, they're very similar to calcite, that they don't really interfere with its strong plain polarised light colour. And the effect of that is that it looks almost identical in plain polarised light and in cross polarised light. So if you see a mineral that doesn't appear to change at all when you flick from plain to cross polars, then that is really, really useful for picking out titanite, which you might also know as sphene. That's the old name for it, which a lot of people still like to use. So we've dealt with standard interference colours, but there are also a couple of minerals that show anomalous interference colours, which is very naughty of them. One of them is quite common, particularly in metamorphic rocks, and it is chlorite. So chlorite up here, these are plain polarised light views at the top and cross polars at the bottom. On the left-hand side, we've got metamorphic chlorite, and this is chlorite, a mass, really kind of messy mass of very indistinct crystals. Pale green colour, if you use the eye of faith, and that is breaking down the garnet on the right-hand side here. And the interference colours of the chlorite in this case are a kind of horrible, inky, murky brown. And you can see from the way that they are a kind of felted mass that they are they're very, very different from the kind of standard interference colours you'd expect. But anomalous colours, I said there wasn't going to be any theory, and part of the reason for that is that I don't know most of this stuff very well. So the anomalous interference colours, it's where the colours that you see in cross polars don't match what they should be for the birefringence value of chlorite. So all anisotropic minerals have this birefringence value, which I think is to do with the difference in refractive indices, and that produces interference colours. Chlorite has a particular birefringence value, but that value does not match the colours that it shows. Now, I don't know why that is, unfortunately. The colours don't fit the chart, Claire says. That's a much better way of putting it. So when you see colours that don't fit the chart, that you can't sort of fit them into the neat birefringence colour chart, then you just have to call them anomalous. Even worse, chlorite doesn't just have one anomalous colour. It's not always brown. It can be really quite a nice blue colour, a sort of inky blue. And this is chlorite here on the right-hand side, which is actually altering biotite in an igneous rock in a granite, and that's a very common texture to see. So chlorite can be brown or blue, and it can even be grey as well. So it's a real pain. Another one with anomalous interference colours is chloritoid. So chlorite and chloritoid, they sound the same, and they both have interference colours which are anomalous. So this is this kind of ragged skeletal crystal here, which has got lots of inclusions in, so that's why it looks quite ragged. A sort of bluish or greenish colour, pleochroic in thin section, in plain polarised light, and in cross polars you have a sort of inky, greyish, bluish, greenish colours. They vary quite markedly, but they're always anomalous. They always have that kind of inky, washed out look to them. And if you use the eye of faith on this, you can actually also see that there are stripes of this colour in this one crystal here, and that reflects lamellar twinning, a bit like plagioclase, but it's rarely so well defined. It's not the kind of pinstripes, but you can see stripes of colour running down chloritoid crystals, and those are lamellar twins.